In our first section, we'll cover electrochemistry and batteries. Electrochemistry brings together the study of two separate domains, that of electricity and of chemical reactions. The same electrons that are so critical to chemical reactions are also responsible for the flow of electricity in electric circuits. The first electric generator worked by using a machine to create static electricity by rubbing dissimilar materials together. It was not connected to chemistry. So, for hundreds of years, chemistry and electricity were studied separately. The connection between them first emerged due to experiments by Galvani in 1791. He noted that a frog's muscle would twitch when touched by two metals. He wrote that this was a special biological electricity. Volta and others later proposed that this was the same electricity that had been observed earlier, but was generated by two dissimilar metals being in contact with the fluid in the frog. Those dissimilar materials in an electrolyte generated electricity, which made the muscle twitch. Volta in 1800 proved that dissimilar metals in an electrolyte would generate electricity and built the first electrochemical battery of sorts. It used zinc and copper plates separated by cloth soaked in a briny salt water. You can see an image of the battery type thing on the right, where we have different loops of these different metals, and here you can see the alternating zinc and copper on the more animated photo. And then in between is the soaked salty water, or the electrolyte. So your traditional battery that you buy from the store and use is the modern version of Volta's design. The copper top is just used to market the brand of the battery, but dates back to that early voltaic cell made by Volta. So below you can see how instead of being lined up, the zinc and the copper are now rolled together. Okay, so you have these rolls of zinc and copper with the electrolyte between them. On a battery, the positive terminal is called the cathode, and the negative terminal is its anode. Electrons naturally flow from the negative terminal to the positive terminal, from anode to cathode. By connecting electrical devices between the terminals, the battery powers them. Of course, if you have some background in electrical circuits, conventional electric current flows in the opposite direction from positive to negative due to the direction being defined before it was known that electrons have a negative charge. The theoretical electric potential difference between the anode and cathode, or between the terminals of the battery, is called the battery's electromotive force, or EMF. The electromotive force is what drives or pushes the electrons through a circuit. The more EMF, the more force is exerted on each electron. It's also called the cell potential and is designated E sub cell and is measured in volts with a capital V. The volt is a measure of the difference in electric potential energy per unit charge at two different locations, in this case between the anode and cathode. 1 volt is the electric potential required to impart 1 joule of energy to a charge of 1 coulomb. In other words, 1 volt is equal to 1 joule per coulomb. The electric potential difference between the anode and cathode is the driving force that pushes the electrons, the EMF. In a voltaic cell, which we will be studying in this chapter, the EMF, or electromotive force, is called the E sub cell. E sub cell, or the cell potential, is measured in volts, abbreviated with a capital V, where 1 volt equals 1 joule per coulomb. In a spontaneous reaction, the cell potential is positive. The EMF depends on the cell reaction involved. Under standard conditions, remember we're talking about a concentration of 1 molar, pressure of 1 atmosphere, and temperature of 25 degrees Celsius. And if we're talking about standard conditions, then often we see reported a standard cell potential, E with the subscript cell, so for our cell potential, but then remember we have this superscript 0 here for standard conditions. The development and improvement of batteries is on the cutting edge of improving sustainable human life on Earth. New improved batteries make things like watches, laptops, tablets, energy storage created by wind and solar power, energy for hybrid and electric cars, energy for drones and other mobile devices, and many more innovations that we haven't heard of or thought of yet. There's ongoing research in this area on improving batteries from very small to very large for all these purposes and more. Improving batteries will be a major field of study for the foreseeable future. The efficiency of real batteries is critically important. When a battery is used, it generates heat, which is not useful for doing work. The efficiency of a battery is the percentage of its electric potential energy which does work and that doesn't generate heat. The more efficient the battery is, the more work it can do, and the less heat it generates. We now depend on batteries being rechargeable, whether it's the battery in our car, which gets recharged by the alternator when driven, or that of our phones, laptops, or tablets, which we charge at night, or the storage battery used during the day to store energy from solar cells for use at night. The capacity to be recharged depends on the electrochemical reactions in a battery being reversible in an efficient manner. Efforts are underway to make recharging faster and more efficient. Why not have electric car and phone batteries that could recharge in a few minutes rather than hours? For many applications, the amount of energy which can be stored in a battery of the smallest size and mass is critical. This is the energy density of a battery. If the energy density of batteries in electric cars could be doubled or tripled, their range would be as well, making them very much more competitive with gasoline-powered cars. If we could travel 1,000 kilometers on a single charge, recharging only took minutes, electric cars would be much more competitive. This all comes down to improving battery technology, which is all about electrochemistry. Electrochemistry goes beyond batteries, though. It also explains how we can electrolyze water to store energy until we get it back by burning the hydrogen back into water or powering fuel cells. Electrochemistry also explains how we prevent corrosion or rusting of cars, ships, and any exposed metal, and explains how we can plate materials with a metal surface. But we'll begin our study of electrochemistry with batteries, where it all began.